أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله. Thanks for Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Which of the blessings of your Lord will you both deny and son deny? We need to make shukr to Allah subhanahu wa ta'ala who has created us in the Ummah of Hazrat Muhammad sallallahu alayhi wa sallam. The best of all the Anbiya alayhim Islam, they came to existence to guide the humanity since Adam alayhi Islam till the last messenger Muhammad sallallahu alayhi wa sallam. We also need to make shukr to Allah subhanahu wa ta'ala who has given us iman, to believe Allah subhanahu wa ta'ala with all his powers, with all his qualities, with all his control. It comes in a hadith more or less meaning 70 branches. The exterior most is the one of saying La ilaha illallah. There is none worthy of worship except Allah subhanahu wa ta'ala. And the inferiormost is the one of removal and obstacle from the way. Modesty, haya, is also a branch of iman. Today is 9th of December 2020, and we are taking into consideration infinite sequences and series. We got an idea about sequences, their convergence, divergence. So we have seen that it all based upon the nth term. The most vital is going to be the nth term. If the nth term converges, we say that the whole sequence is going to be convergent, otherwise divergent. So in the loose term, we could say that if the outcome to the nth term is finite real value, we say that it is going to be convergent, otherwise divergent. Pretty much on the same line, when we talk about the convergence or divergence of a series, we need to rely on the nth partial sum. So based upon the convergence or divergence of the nth partial sum, we describe the convergence or divergence of the whole series. Today we are going to talk about alternative options to observe the convergence or divergence of a series. We will be having quite a few tests. Based upon those tests, we will describe the convergence or divergence of a particular series. But before we move on, we have a definition about a series. We say that a series is said to be a positive term series or a series of positive terms if every term has positive value. If an is greater than 0 for all sort of values of n. And we know that what is n? N belongs to the set of natural number or all positive integral values. So whatever the value of n, the term of the series should have positive value. N is equal to 1, 2, 3, 4, 5, and then so on. So all sort of terms will be having positive value. So if every term is a positive term in terms of its value, we say that the whole series is a positive term series or a series of positive terms. So it is vital to describe this one because this is going to be one of the criterion before we look into the implementation of certain tests. Description is there before we move on. What we have done so far, in order to examine the convergence or divergence of an infinite series, we need the nth partial sum of the series. The trouble with the nth partial sum of the series is that for most of the series, it is very hard to find a simple formula. Therefore, we formulate tests to check the behavior of a series by considering its nth term rather than looking into the nth partial sum of the series. We will take into consideration the nth term, just like we got an idea about the convergence or divergence of a sequence. The convergence or divergence of a sequence is based upon the convergence or divergence of the nth term. So we are going to develop certain criterions behind the scene. Certain tests are there to observe the convergence or divergence based upon the nth term of the series, rather than looking into the nth partial sum of the series. But there is one drawback with all these tests, that they will enable us to see the convergence only. Previously, we have seen that if a series is convergent, we can also approximate its sum from the nth partial sum. But with all these upcoming tests, we will only observe the convergence or divergence. And these tests will not provide convenient formulas to find the sum of convergent series. So this is going to be a drawback behind the scene. Won't be able to do that. But if you are interested to do that, so you need to go back and see if you got a formula for the nth partial sum, reasonable expression is there. So we will be happy to see the sum of that convergent series. Otherwise, for the upcoming test, we will just observe the convergence or divergence of the series. So take a look to the first test, Cauchy's integral test. Before we look into the implementation of this test, we have to fulfill certain criterion. We need to look into the prerequisites to be fulfilled before we look into the implementation of this integral test. Remember, there is not a unique technique in the world which is going to be applicable to each and every phenomena. Every technique has got some merits, demerits, so applicable to certain phenomena, whereas for other phenomena, some other suitable techniques are there. So before we look into the implementation of Cauchy's integral test, we need to see, number one, whether the series is a series of positive terms or not. We got a definition to that. Positive term series. If every term is positive, means the value is going to be positive value for all sort of values of n. So such a series is said to be positive term series, that every term is of positive value. Secondly, f is continuous and non-increasing function over the interval from 1 to infinity. What is f going to be? F is corresponding to, pretty simple to take an expression for f from the nth term. So keep an eye that f is the nth term for the time being. Later on, we will see how do we take f from the nth term. So just imagine for the time being, the nth term is basically there for the series, and we will take f from the nth term. So the first thing we need to observe whether the series is a positive term series. Secondly, corresponding to the nth term, f is continuous and non-increasing on the interval from 1 to infinity. So somewhat it is in accordance with the values to n 1 to infinity. So the interval is a half closed, half open. From the left hand side it is closed because the left boundary point is going to be a part of consideration, whereas the right hand point by default it is not going to be a part of consideration. It's infinity. Infinity is not a real number. It's a symbolic representation for things go on forever beyond our comprehension. So half closed, half open interval is there. So over that interval, we need to see the continuity. Continuity, we know that. The criterion is there. Graphically, to observe the continuous function, if you plot the graph without lifting the pen up and complete the portion of the graph, it is going to be a continuous one. Analytically, criterions are there. We need to fulfill 3 of the conditions. It should be defined. It should have a limiting value. And then the third and most vital property is that the limiting value should be equal to the numerical value at the target point. And then secondly, non-increasing function. We have an idea about increasing and decreasing based upon the application of derivative. One of the prominent application of derivative is that it will tell the behavior of the function to be increasing or decreasing. So based upon the sign of the first derivative, if the sign of the first derivative is positive, we say that the corresponding function is going to be increasing. And if the sign of the first derivative is negative, the corresponding function is to be decreasing. So non-increasing. It's pretty hard to observe that, but surely if a function is decreasing, surely we are on the safer side. So if it is decreasing, surely it is going to be non-increasing. Have a look. We have gone through with this idea. Monotonic sequences, just an idea, take an idea. Non-decreasing sequence, if every upcoming term is going to be greater than or at least equal to the previous term. So when we arrange terms of a sequence, so it has to be a pretty systematical arrangement of those elements, of those terms. So not necessarily that every upcoming term is going to be greater than the previous one. For example, partway through in finally many terms of a sequence, if 2 consecutive terms are of equal value with this equality sign, so then it is not going to be decreasing. So it is not going to be increasing because every upcoming term is going to be greater than the previous one, means the corresponding sequence is going to be increasing. But with this equality sign, surely it is going to be non-decreasing. If you take this equality sign out, so we say that surely it is going to be increasing. That every upcoming term is going to be greater than the previous one. So with this equality sign, we say that it is going to be non-decreasing. Not sure whether it is going to be strictly increasing or not, but surely a non-decreasing. But if you look into those 2 aspects, strictly increasing, strictly decreasing, we have no equality sign. every upcoming term is going to be greater than the previous one. And the last case, every upcoming term is going to be smaller than the previous one. So we, rather than look into this one, if for example, if you follow that criterion, sequence is strictly increasing, so surely it is going to fulfill this criterion, non-decreasing. To the other end, to justify that non-increasing, if we say that it is strictly decreasing, surely it is going to fulfill automatically that criterion. So keep an eye on second and fourth. We will try to figure out that one, strictly decreasing, and we know the criterion. What the criterion is there? One of the prominent application of derivatives based upon the sign of the first derivative. We will see that whether it is decreasing or not. If it is decreasing, surely it is going to be non-increasing. So again, three things that we need to justify. We need to fulfill those criterions before we look into the implementation. Number one, series has to be positive term series. Secondly, corresponding to the nth term, f should be continuous and decreasing, non-increasing. I mean, we will justify that by taking into consideration decreasing on this interval from 1 to infinity. Continuity can be observed in many ways. Analytically, we are interested to see if there is any troublemaking value. Troublemaking value is going to be the value which makes the function undefined. So simply, if there is a polynomial, no harm is there. There won't be any trouble with that. Yes, the trouble would be there if there is a fraction most of the time, and we see the denominator is going to be 0. For those values that make the denominator equal to 0 are going to be troublemaking values. So this is another way or alternative way to look into the continuity, see those troublemaking values, whether they do exist or not. If they are, so we say that the function is going to be discontinuous because the corresponding value of the function won't be there. So we say that if these three criterions, positive term series, f is continuous, decreasing on that interval, we say that yes, we can apply Cauchy's integral test. What the test says about the convergence or divergence of this series, we say that this series is going to be convergent if this integral converges. Integral over the interval from 1 to infinity. So f is going to be observed from the nth term. Corresponding to the nth term, f will be there. So we will observe the convergence of this integral. And the series is going to be divergent if this integral diverges. So simply we will observe whether there is going to be finite real value as an outcome or not. If it is there, we say that yes, the series is going to be convergent or it will be divergent. But before we look into the implementation, we have to fulfill these three criterions. Take an example. We have gone through with this one. Harmonic series is there. We need to see whether this series is a convergent series or not by implementing the Cauchy's integral test. But before we look into the implementation, we need to fulfill those three criterions. The series should be positive term series, and then f corresponding to the nth term. Have a look at this one. An being the nth term is equal to 1 upon n. So corresponding to that, f of x would be 1 upon x. So just simply replace n by x, it will be f. F is corresponding to the nth term. To do with that, just take an and replace n by x. So it will be corresponding f. So first criterion, series should be positive term series. So have a look at the first term by taking n is equal to 1. So the first term is 1 upon 1, positive value. By taking n is equal to 2, the second term would be 1 upon 2, positive value. For n is equal to 3, 1 upon 3. So we see that yes, and so on, it is going to be positive term series. What about this function? Is it continuous or not? So rather we'll look into each and every possible real value. We'll look into the troublemaking values. What the troublemaking value is, x equal to 0. But we see that x equal to 0 is not going to be part of the interval 1 to infinity. So it means that all sort of values are going to be acceptable values, x greater than or equal to 1. The only troublemaking value which makes the function undefined is 0, but this is not going to be the point of consideration. So we are on the safer side, because for all sort of values of x greater than or equal to 1, or over the interval from 1 to infinity, it is going to be continuous. There is no point of discontinuity. Then third property, we need to see whether it is decreasing or not. So how do we observe? Take its first derivative. The first derivative would be minus 1 upon x square. So minus 1 upon x square for all positive values of x. So because of negative sign, minus 1 upon x square, the outcome is going to be negative. So indicates that f is decreasing. So you can do it sideways, otherwise it can be observed directly from the given expression. From the given expression, we say series is positive term series. There is no point of discontinuity over the interval from 1 to infinity. Third property, take its derivative. Derivative is minus 1 upon x square. Since derivative is negative, we say that the function is going to be decreasing one. So all three requisites are done. So we can apply integral test now. Cauchy's integral test. It's an integral from 1 to infinity. Remember, it's an improper integral. One of the limit is going to be infinity. So we replace infinity by a parameter t. T approaches to infinity. So 1 to t, where t approaches to infinity, we'll look into the integral of f with respect to x. What is f? F is equal to 1 upon x. So integral to 1 upon x is going to be natural log of x. Apply the upper and lower limit. At the lower limit, it is going to be 0. At the upper limit, natural log of t. So t approaches to infinity means we do not have a finite real outcome. Integral diverges. Since the integral diverges, so it means that corresponding series is going to be a divergent series by using Cauchy's integral test. That one, the second one. Since this integral diverges, the corresponding series is going to be a divergent series. So merely you can see it's a matter of finding integral. Mainly based upon the integral, we will observe the convergence or divergence of the whole series. If the integral converges, the given series is going to be convergent. Otherwise, it is going to be divergent. So we took an example. of a harmonic series and see that it is going to be a divergent series. We take a generalized case, which is known as P series or hyperharmonic series. 1 upon n raised to power p. We know about n. N is from 1 to infinity. There is no restriction on p. P is a real constant. But if you closely look into the real line, we can split into 3 pieces: positive values, negative values, and 0, neither positive nor negative. So we will be having 3 pieces for p to be positive, negative, 0 over there. If you add 0 to the positive values, we say that non-negative values are there, 0, 1, and then so on. Those values are going to be, real values are going to be non-negative. So we need to look into those possibilities for all sort of values of p to be real value, positive, negative, as well as 0. So we need to consider those cases. And then we have to observe the convergence or divergence of this series. This is going to be very, very prominent series to be discussed because many of the expression could directly be observed by taking into the consideration of this P series. So first of all, we look into the convergence or divergence of this series. If you take P less than or equal to 0, because P is going to be real, could have positive values, negative values. 0 could be included to negative values or to positive values. So we take into consideration with the negative part. So if P is less than or equal to 0, then apply the divergence test. What the nth term test for divergence of a series? If the limiting value to the nth term is different from 0 or fails to exist. To the nth term fails to exist or the limiting value to the nth term is non-zero, we say that the series is going to be divergent. What the nth term is here, 1 upon n raised to power p for all sort of values of p less than or equal to 0. If you take p is equal to 0, so something upon n raised to power 0 means it is going to be non-zero answer. Or you can take that denominator into the numerator because the power is negative. So bring it in the numerator and then apply the limit. So in both cases, we say that the series is going to be divergent by using nth term test for divergence. What the nth term test for divergence? Have a look. That one. Series is said to be divergent if the limit to the nth term fails to exist, or it does exist as a finite real value, but is different from 0. In both cases, we say that the series is going to be divergent. So that's what we look into. And say that for all sort of values of p less than or equal to 0, this series is going to be divergent. Still, we have to look into positive values, remember, greater than 0. Which shows that the above series is divergent series. Now we look into the values of p greater than 0. For all sort of values of p greater than 0, we take f corresponding to the nth term, 1 upon n raised to power p. F of x would be 1 upon x raised to power p. So we need to see whether it is going to be positive term series Yes, surely it is going to be positive term series because n varies from 1 to infinity. P is positive. So by taking any value of going to be positive. Is it continuous? Surely it is continuous. Again, the point of discontinuity is not going to be a part of consideration. Is it decreasing? Yes, pretty much like we have seen in the previous case, 1 upon x. So it is 1 upon x raised to power p. So if you take its derivative, it is going to be negative for all sort of positive values of x. So we say that all three criterions are fulfilled. Otherwise, you can do it sideways. Check one by one, all those three criterions. Since all the criterions are fulfilled, we can apply integral test, Cauchy's integral test for all sort of values of p greater than 0. So integral test from 1 to infinity. So take that factor and bring it into the numerator. So x raised to power minus p. So take its integral, derivative is available, so increase the power by 1 and divide it by that power, minus p plus 1. At the upper limit, we will be having this expression. For the lower limit, it will turn out to be that one. Constant value won't be affected by the limit. So we are interested to see the convergence or divergence of the given series corresponding to p greater than 0 by using the integral test. So we need to see the outcome. Is it going to be finite real value or infinity? So what are the possibilities behind the scene? It all based upon this exponent. We know that if the exponent, that power of t, is negative, you can take that factor and bring it in the denominator. So once infinity is there in the denominator, so something finite upon infinity, it is going to be 0. And you will be having finite limiting value 1 upon 1 minus p for any positive value of p. The outcome is going to be positive. The outcome is going to be finite real value. So in this case, you will see that yes, integral converges if the exponent is negative. Because in this case, you can bring this factor in the denominator and then apply the limit. This term will be vanished, the first term, and you will be having that one, which is going to be finite real value corresponding to any positive value of p. So which shows that this limit exists if the exponent of t is negative. That is, this whole thing minus p plus 1 should be less than 0. Negative should be less than 0. So in other words, we say that p should be greater than 1. From this inequality, get the value p. P should be greater than 1. So what we have obtained, first of all, we say that it is divergent for all sort of values of p less than or equal to 0. So less than or equal to 0. Now we say that it is going to be convergent for p greater than 1. What about p equal to 1? Because p is less than or equal to 0 and p is greater than 1. What about p equal to 1? So the improper integral converges if p is greater than 1 and diverges if p is less than 1. What about p is equal to 1? I mean, have a look at the exponent. If it is negative, convergent. If it is positive, divergent. And if it is positive, it means that p is going to be less than 1. So less than 1, all sort of values of p less than 1. And then this part of the interval, less than or equal to 0. So combine this one with that one. Now we say that it is divergent for all sort of values of p less than 1 and convergent the given series for all sort of values of p greater than 1. What about p equal to 1? So if p is equal to 1, so it will turn out to be 1 upon n, the harmonic series, and we already have seen that. 1 upon n raised to power 1 being harmonic series is a divergent series. So this p is also combined with that one. So eventually we say that hyperharmonic series, p series, is going to be convergent for all sort of values of p greater than 1 and divergent for all sort of values of p less than or equal to 1. So we note down this expression. It's pretty vital. Have a look. It's a hyperharmonic series n raised to power p. What is n? N varies from 1 to infinity. We say that it is going to be convergent or divergent or convergent.
Sir, please turn on your camera, sir. We can't see the blackboard, the whiteboard.
Okay. Sorry for that. So I need to adjust it. So we say that this p series 1 upon n raised to power p with an extra and varies from 1 to infinity is going to be convergent or divergent if p is greater than 1 and if p is less than or equal to 1. So based upon the value of p, we will look into the convergence or divergence of this whole series. So very powerful result is there. We need to keep an eye on this result. It's going to be utilized over and over again. While talking about a few examples from the exercise, we can directly look into the convergence or divergence. For example, as an example, we are interested to see the convergence or divergence of this thing. Is it going to be convergent or divergent? So based upon p, what is p? Is equal to 2.
Excuse me, sir.
Yes, please.
सर आपकी आवाज में डिस्टॉर्शन बहुत है.
It might be at your end because of the internet issue. I mean, sometime, of course, because of the speed of the internet, it could be. But anyway, recorded will be forwarded to you. So we are interested to see the convergence or divergence of this series. For example, as an example.
सर आपके एंड पे इंटरनेट का काफी इशू है.
Okay, it's fine. Could be.
यार हमें तो ठीक आ रही है.
यार आपकी तरफ होगा, हमारी तरफ सही आ रही है.
तुम्हारी तरफ तो ठीक है.
Okay, please mute your microphone. If there is an issue with your end or whatever the issue is, afterwards the recording will be forwarded to you, so you can look into that. So for example, 1 upon n square is there. What is p here? P is equal to greater than 1. So directly we can say that it is going to be convergent because it's a p series with p greater than 1. So no need to check anything. So very powerful result is there. We can directly look into the convergence or divergence based upon the value of P. If P is greater than 1, convergent. In other words, if it is less than or equal to 1, so we say that series is going to be divergent.
सर कन्वर्जेंट सीरीज में ग्रेटर देन है या ग्रेटर देन इक्वल टू 1 है?
Less than or equal to 1 is divergent.
No sir, in convergent series sir, is it greater than equal to or only greater than 1?
Greater than 1, because 1 has been added to less than or equal to. So in this way, we say that P series is going to be very helpful for many of the cases where we can see if the nth term is compatible with 1 upon n raised to power p, we can directly look into the convergence or divergence based upon this convergence or divergence of this P series. So P series is going to be convergent for P greater than 1 and divergent for all sort of values of P less than or equal to 1. So you see that equality sign is only taken once. Either it is going to be with this one or that one. Since we have with that one, P is less than or equal to 1. The other one is surely inequality. It is convergent, that one, for P greater than 1, strictly greater than 1. Divergent for P less than or equal to 1. Because if P is equal to 1, it's harmonic series. And we have seen that harmonic series is a divergent series. So this is all. P is equal to 1 is combined with P less than 1. So it will turn out to be P less than or equal to 1. So now we take a few examples from the exercise. Take into consideration exercise number 10.3. Use the integral test to determine if the series in exercises from 1 to 10 converge or diverge. So we need to apply the integral test. But before you apply the integral test, Cauchy's integral test, we need to check that the conditions of the integral test are satisfied. What are those conditions? Number 1, the series should be a positive term series. Secondly, f of x corresponding to an should be continuous and decreasing. If these three criterions are fulfilled, only then we can look into the implementation of the integral test. So I give you an idea. For example, this one. First criterion, is it going to be positive term series or not? Take only a few of these values of n. For example, n is equal to 1. Yes, 1 upon 1 square, positive. For n is equal to 1 upon 4. For n is equal to 3, 1 upon 9. So all these values are positive values. So it's a positive term series. Is it continuous? Yes, it is going to be continuous because the only value which makes the function undefined is going to be 0, and 0 is not a part of consideration because we need to look into the interval from 1 to infinity. Is it going to be decreasing? So take its derivative. 1 upon x square would be f of x. So take its derivative. So it will turn out to be minus 2 upon x cube. So minus 2 upon x cube. X is positive. So because of this negative sign, the overall expression would be negative. So all three criterions are fulfilled. Otherwise, you can do it sideways. check one by one those three criterions. So since those criterions are fulfilled, then you look into the integral. Integral over the interval from 1 to infinity of f of x. F of x would be 1 upon x squared. So it's a matter of finding integral. Then based upon the value of the integral, if integral converges, this series is going to be convergent, otherwise divergent. One of the, pretty much on the same line, you can look into them. The most technical question is going to be question number 9. Because you have to bring one more concept into example number 9. So have a look. Is it going to be positive term series? Yes, obviously that. Because for all sort of values of n, it is going to be positive, 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 positive. All sort of positive values. Secondly, is it going to be continuous? Yes, there is no trouble making value. There is no trouble making value. It is going to be continuous. Now, is it going to be decreasing? That's what we need to see. You try yourself and calculate the first derivative to f of x. F of x is equal to x squared upon e raised to power x, x upon 3. You try to calculate the first derivative. I do check that. F of x is equal to x squared upon e raised to power x upon 3. Take its first derivative and then see whether it is going to be positive or negative for all sort of values of x. Remember, x is basically n behind the scene. And what is n? N varies from 1 to infinity. So check its first derivative. You can also utilize the quotient formula or whatever you try to figure out the first derivative of f. Right, have a look. Have a look on the sideways board. I try to figure out. So our series is basically that one. N varies from 1 to infinity n squared upon e raised to power n upon 3. So we need to see the convergence or divergence of this series. So what we see corresponding to that, f of x is going to be xk upon e raised to power x upon 3. So we select the given series is positive and also continuous. The given series is positive because every term is going to be positive for all sort of values of n greater than or equal to 1. It is also continuous for all sort of values of x. Okay, no fear is there. So we see that it is called for all sort of values of x greater than or equal to 1. The given series is a positive term series. If you look into the first derivative, f prime of x, so f prime of x is equal to, if you combine the expression, it will be minus x into x minus 6 upon 3 times e raised to power x upon 3. You can double check. So a prime of x is something minus x times x minus 6 upon 3 times e raised to power x upon 3. So we need to make it negative. For what values of x, it is going to be negative. Have a look one by one. If you take x equal to 1, what is x? X is basically corresponding to n. N1, 2, 3, 4, complete values are there. So if x is equal to 1, negative value, 1 minus 6 minus 5, minus 5 into minus 1, positive value. So the answer is going to be positive for x is equal to 1. For 2, again negative. For 3, again negative. 4. What about 6? Makes it 0. So we are in that it is going to be negative for all sort of values of x greater than 6. So the sign of the first derivative would be negative when x is going to be greater than 6. What the next value, complete value to be considered for x, which is greater than 6, we say that it is going to be greater than or equal to 7. So you need to take start from 7 as a complete value, greater than 6, but as a complete value, it is going to be 7. So we see that f is continuous and positive term series for all sort of values of x greater than or equal to 1. But it is decreasing for all sort of values of x greater than or equal to 7. So the combined interval to be considered by fulfilling all 3 requirements is going to be that one. We cannot consider this one because 1 is not going to be a part, 2 is not going to be a part. So only we can consider the values of x which are greater than or equal to 7. So in other words, we need to implement the integral test against this interval. We cannot look into the integral from 1 to infinity because all 3 requirements are going to be fulfilled only for all sort of values of x greater than or equal to 7. So this is how we will take into consideration this interval. So based upon the convergence or divergence, you need to see whether it is convergent or divergent. Look into the integral. I give you an idea of what the troublemaking value is here. Assume that it is going to be convergent. Assume that. Eventually we see that if it is convergent. So this integral converges to a finite field value. So the corresponding series, that one from n equal to 7 to infinity n scale e raised to pi n upon 3 is going to be convergent. Since this integral converges, so we say that that series is going to be convergent and varies from 7 to infinity. But the given series is going to be that one. What about this one? So have a look. We write it down, this one, in that fashion. So n varies from 1 to infinity. Expand this one by taking n is equal to 1. So it will turn out to be 1 upon e raised to power 1 upon 3. For n is equal to 2. It will be 4 upon e raised to power 4 by 3. Plus for n is equal to 3, 4, 5. 6 when n is equal to 6. So it will turn out to be 36 upon e raised to power 6 by 3 plus that one. And varies from 7 to infinity n scale e raised to power n upon 3. So we can expand this one. Since we know that that one is convergent and we have finite number of terms over there, 6 of them in fact. If you go back to the previous lecture and see one of the remark, very powerful remark, that if you add finite number of terms to a convergent series, the convergence of the series won't be affected. Or if you delete finite number of terms from the convergent series, again the convergence won't be affected. Convergence or even divergence won't be affected by adding or deleting a finite number of terms. So what we see? This series is equal to term number 1, 2, 3, 4, 5, 6, and then the rest of all the terms from 7 to infinity is going to be convergent because that part of the series, you can say that sub-series, is convergent and we add finite number of terms to a convergent series. So that series is going to be convergent. So not only you need to see the convergence of sub-series, but also you need to bring the concept from the last lecture, if you remember. Take a look at the.
Sir, please.
Take a look. Have a look at this remark. We can add a finite number of terms to a series, or we can delete a finite number of terms without altering the series convergence or divergence. So if a series is convergent, we can add finite number of terms or delete finite number of terms. The convergence of the series won't be affected. Same is the case with the divergence. So that's what we say. In fact, we are talking about this example. 9. we are interested to see the convergence or divergence of this whole series, but we see that all sort of values of n from 1 to infinity, they are not going to be considered to fulfill those three criterions. Those three criterions, number one, positive term series. Secondly, f corresponding to an is continuous and decreasing against all sort of values of n greater than or equal to 7. So we start from n is equal to 7 and look into the implementation of integral test. Integral test, I mean, we presume that the answer is finite. The integral converges. Then we say that series with n varies from 7 to infinity is going to be convergent. But what about that one? It varies from 1 to infinity. So we expand first 6 terms and rest of them from 7 to onward, we take as a part of this series. And since the answer to that is convergent and the first 6 terms are added to a convergent series, the overall series is going to be convergent. Yes, please. What's your query? Is there any question, please? Yes, 27.
Sir, the criteria for checking continuous convergence and divergence would be 3 conditions that you have told.
No.
And
It's
how will
basically
we check the continuous or it is continuous or discontinuous?
Have a look. I take your question. Those 3 criterions are basically to be fulfilled before we look into the implementation of the integral test. If those criterions are not fulfilled, at least one of them is not fulfilled, we cannot implement integral test. In the statement, it is given that use the integral test. And before you use the Cauchy's integral test, be sure to check that the conditions of the integral test are satisfied. So once the conditions are satisfied, only then we can look into the implementation of the integral test. So those 3 criteria are basically to check whether we can apply the integral test or not. If the criterions are not fulfilled, we need to search an alternative option rather than implementing integral test. Since we have to apply, so we need to fulfill them. And how do we check the continuity? Plenty of ways we can check that. If you remember from the starting lectures, geometrically, we look into the graph. If there is no pointer missing, we say that the corresponding portion of the graph is going to be continuous one. Pretty simple idea is it. If you start plotting the portion of the graph without lifting the pen up and complete the portion of the graph, the portion of the graph would be considered as continuous. Analytically, basically there are 3 criterions. Number 1, function should be defined, should have a limiting value, and then the limiting value should be equal to the numerical value. So rather than we check each and every value, for example, in this case, n is equal to 1, 2, 3, 4, 5, infinitely many values are there. Rather than we check all those values, whether the function is defined or not, we come round the way. It's much more convenient. We look into those values which make the function undefined. So have a look at 1 upon n squared. What are those values of n which make that expression undefined? It is going to be 0. So other than 0, all sort of values are going to be acceptable values. Since 0 is not going to be part of consideration, so we say that for those considered values, it is going to be continuous because there is no troublemaking value. So this is how we can check the criterions. Once the criterions are fulfilled, only then we can look into the implementation. Take a look. Before we move on, I take your attendance. So we got 133 participants at present. Let me double check. Yep, it's done. Have a look at another set of examples from 11 to 40. Which of the series in exercises 11 to 40 converge and which diverge? Give reasons for your answer. When you check an answer, remember that there may be more than one way to determine the series convergence or divergence. No, there is no restriction that you need to apply the integral test. So you can check it by any technique or any criterion developed so far. Now, what are the options behind the scene that you can check? We can see whether the series is going to be geometric series or not, or one of the option is there. If it is geometric series, then we need to see the common ratio, if it is greater than 1 or less than 1. Based upon the common ratio, if it is less than 1, the series, geometric series, is going to be convergent. We can look into the nth term divergence test, look into the limiting value to the nth term. We can look into the option of P series as a third option, whether it's a P series or not. You see that one is a P series. Have a look at this one, 3 upon n raised to power 1 by 2. So you can take 3 out of that expression, it's common value. So 3 fixed value is there. So 1 upon n raised to power 1 by 2. And we know that from the P series. P series is convergent for all sort of values of P greater than 1. For all sort of less than or equal to 1, it is divergent. So P is equal to 1 by 2, less than 1. So you can directly say that it's a P series with P is equal to 1 by 2, less than 1. So it's a divergent series as an option, because you could have more than one way to determine the series convergence or divergence. And the last option is the Cauchy's integral test. So now you have 4 options to be implemented. You can try any one of them. Like in the first case, we see that if n is equal to 1, it will be 1 upon 10 raised to power 1. For n is equal to 2, the second term would be 1 upon 10 raised to power 2, then 1 upon 10 raised to power 3, and so on. So it's a geometric series with common ratio 1 by 10, less than 1. So it's a convergent geometric series. So this is all. You need to just identify whether the series is convergent or divergent. You can also look into this one. It's also geometric series. But have a look at this example. Number 13, n upon n plus 1. So apply the limiting value to the nth term. So you can apply nth term test for divergence. See the limiting value. So I presume that it's an indeterminate form initially, but then dividing by n, it would turn out to be 1. The answer would be 1. The limiting value to the nth term as n approaches to infinity is going to be non-zero. So you can say that by using the nth term test for divergence, it is going to be divergent series. So you need to give reason, you need to justify, because more than one option. Whether the series is convergent or divergent. If it is convergent, give an argument. How do you justify that? And same is the case with divergence. Because you have more than one options, you need to justify by utilizing the criteria. So I would say at least 30 questions you can try, 30 examples, 1 to 30 of this exercise. 1 to 10 are there, and then another 20 questions you can try. It's good enough for practice purpose. All right, so that's it for today's lecture. If you have a short query, as we left with a couple of minutes only.